PowerPoint here. Okay, I'm going to start out with a PowerPoint. As boring as those things are, but he has some pretty good pictures in there, pretty good descriptions. Oh, valid, no problem. Okay. Okay, so let's start. Let's start here. Fan selections. I got some notes too. Okay, so basically, we designed a suction system to pull air away from the worker, contaminated air and contaminants away from the worker. And we used a hood design that was appropriate. We then connected to a ductwork system and to a filter that would carry the air so that it's moving fast enough to transport the material away from the worker through ductwork to somewhere where we can discharge it, get rid of it. Okay, so now before we get rid of it, sometimes we're going to put some sort of device to scrub the contaminant from the air. Two reasons we might want to do that: because the contaminant, we can't discharge it outside legally or something like that, or morally, but usually I'm not too worried about morally, more legally. Or it's some sort of material that could damage the equipment. For instance, if it's an acid gas, it could corrode the fan and so on and so forth. It's an abrasive material, it could corrode the fan blades and so on. So very frequently it'll have some sort of filter or removal device before the fan, and then some more ductwork, and then the fan takes over the brunt of actually causing the air to move. So how does it do that? Well, it's got some sort of device that's going to move air. Two types of fans that we usually run into. One is an axial fan. That's the one that looks like a propeller on an airplane, and a centrifugal fan. This is a centrifugal fan here. So what we're looking at here is basically kind of like a hamster cage, right? It's turning. And the fan and these little plates in here are basically buckets. They're taking air and moving it a bucket at a time, from one spot to another, and air from behind it comes in and takes its place. So this fan is moving air at a certain quantity of air, a certain rate. Okay? And these buckets move, and as they move, they develop a negative pressure on one side of the fan and a positive pressure on the other side of the fan. Because now our negative pressure is governed by what we need the fan to accomplish, right? We're the ones that design this system, and we say that on the suction side of this fan, we need this suction pressure, -4 inches of water, in order to accomplish what we need all the way back through all the contractions, elbows, and all the way back to the hood. That's what we need at that point to overcome all the losses in the system and deliver what we need at the hood. That's really where we need the performances at the hood. But we lose efficiency all the way through. So this has to be able to make up for that. Then it has to take that air and it has to push it out and get rid of it outside. So very frequently, this is going to go to another duct on the other side. Maybe a duct coming out, an elbow, a duct going up, going out through the roof. So you're going to have some resistance to flow going out. Now, if I don't have that ductwork connected, what's the static pressure here? Right? Well, we know the velocity pressure is basically determined by how fast the air is moving. What's the static pressure out here? Zero. It's atmosphere. There's no static pressure. As soon as you leave that fan housing, the static pressure is zero. The velocity, you feel the force of the air, right? Because that's velocity pressure, but there's no static pressure. Nothing for it to push against, right? So that static pressure is zero, right? But the only problem is that very often you can't just discharge from the fan. You need to move it away. If this is on the roof, you might be able to get away with that, right? But more often than not, usually you have to go out and go up so you're at least a certain amount of height over other things that are going on in that roof. If this is if the discharge smells bad, you need to go up high. If the discharge is volatile, you need to go up high. If there are other structures, windows nearby, you need to be a certain height above them and so on. There's a lot of codes that are involved with this, right? So you come out of here, you might have to go straight and then turn and go up through if this is inside the plant, which is not that unusual because you want to protect it from the weather sometimes. So you go out, you turn, go up. So now you have an impediment, an energy loss that wasn't there before. So just like you designed the suction side, now you design the discharge side. So if this is zero static pressure over here, and you go out 10 feet with 12-inch round ductwork, how much of an impediment to that flow does that 12-inch round ductwork give you? 10 feet. You calculate it the same way as you did on the suction side. You can look up K for galvanized iron ductwork, or you use that table 5, and you figure out, okay, well, the K times the velocity pressure, how fast the air is moving through here, let's say that's half an inch. That's at this point here, you have to have plus half an inch in order for it to go through that ductwork. Now you put a turn. That turn might add, how do you know what that is? Or how many sections is it? 90-degree turn. What's the radius of the turn? You look up on chart 5, I think it is. Not chart 5, chart 8, I forget. For elbows, 13. You look up, is it 13? Yeah, you look up K for the elbow, for a specific elbow, times the velocity pressure. Let's say that that's an inch. You lose 1 inch, right? So now you have to generate positive 1.5 inches to get it moving through, because that has to be positive because you're pushing from the fan, not sucking. And then you go up 30 feet with 12-inch ductwork. Maybe just another K times 30 feet times the velocity pressure to get how much that, maybe it's half an inch. So maybe you need 2 inches of positive static pressure to make up for that loss, the energy losses, pushing the air, sucking the air here and pushing it out there so you don't lose the energy on this side.
You're right? The same charts we use?
Exactly the same charts. Okay. You work it exactly the same way, except now you're working with a positive pressure and it's building up over here. This positive pressure is, you're going to start from the fan and work your way out to decide what that's going to be. So at the end of this, what you're going to wind up with, you're going to wind up, I need 4 inches of negative pressure here. I need 2 inches of positive pressure here, right? And so so I'm going through here. There's a change in pressure that this is going to deliver, and I have to move Q. I have to move 2,000 cubic feet per minute of air. So what does that tell you? This tells you how much energy that you have to put in order to get the air moving and to cover any losses on the suction side and on the discharge side. That's determined by your static pressures on the two sides of the fan. And the Q is how much work you're doing, right? You're moving 2,000 cubic feet per minute of air. That's work. Moving it from here, there's so many pounds of air that you're moving at a certain velocity. So you combine those two, and you can figure out how much horsepower, how much energy, how much work that you're doing. Yeah.
Sorry, not related to this. It's just something from the homework that had me on puzzle.
Sure.
You had asked for the volume of air.
Yes.
But I could only give like the cubic foot.
That's volume.
Okay.
Right, cubic feet per volume flow rate. Yeah, I'm never going to be interested in the actual volume of the air.
Yeah, so that's what had me worried.
Oh, I'm wrong. You know, next when we get into indoor air quality and we're discussing dilution ventilation, we're going to be interested in the volume of air in this room. But for this kind of stuff, we're not interested.
Okay,
in
yeah, it had me.
Right. Yeah.
Thank you.
Yeah, that's a volume. That's a volume flow rate. Okay, so figuring this out and is going to help us decide what kind of fan we need and how big a motor that we need for it. And as I mentioned to these guys before, you get a lot of help from charts that the manufacturer produces for the fan and for the motor. And we're going to look at how to use those charts. But trust me, if you actually get into designing one of these systems, if you have a slide hood that you're working with, and you find a manufacturer that makes a slide hood or makes different kinds of slide hoods, and you see one that looks like it's going to meet your needs, they will hold your hand through the design process, right? They have engineering staffs that'll help you out with this. You can do the initial design. They'll review. In fact, chances are, and this is going to be an assignment at the end of the night. I'll give you an assignment for this week. At the end of this whole thing, what they're going to want to do is they're going to want to see your design. They want to review it before they say, yeah, you got the right fan, you got the right motor, and you got the right hood. So their engineering staff will review your design for you. So it'll help you avoid mistakes. Yes.
When was the
I'm sorry. I will probably be due next week, but it's not going to be difficult. Trust me. It's going to be. By the time we get to the end tonight, assuming that I keep my wits about me and we get through this quick enough. It'll be easy, and you'll be able to do it pretty easily. Many versions, right? Many versions, axial and these centrifugal fans and so on. Okay, you see. Okay, so you got centrifugal and you got axial, right? Axial, like the propellers, your shop fan and stuff like that, or the actual axial fan. Axial fans tend to be inefficient and noisy, so you use them as shop fans and stuff like that. Usually in these exhaust systems, you're using these centrifugal fans. Okay, here's an axial fan. Low static pressure. They don't generate a lot of static pressure either, so they're not really all that useful in ductwork. Noising and inefficient. You know, when these things start moving, they really whip the air around. They may be used in ductwork where the air must enter and exit in the same direction. You've seen these inline fans sometimes with no turns or anything like that. So there's a lot of axial fans used in these really inexpensive inline fans. Centrifugal fans either can use a straight blade, or more often than not, they use these plates, these cup plates. And these plates are usually curved, right? And they can spin in such a way that they're curved forwards, or they can spin in such a way that they're curved backwards, right? They both work. One tends to be a little bit more efficient than the other. One tends to be noisier than the other. But they usually either cup forward or cup backwards. And basically, they're just cups moving the air along. Okay, so okay, this one's interesting in that the air enters from the side and exits from the front, so it makes a 90-degree turn in the fan. These are forward curved blades, right? These are backward curved blades. They both work. The backward curved blades are less popular because they tend to get worn. If you're dealing with particulates, they tend to get worn down faster. Okay, here's a backward curved fan. And there's actually, I think the motors, obviously, there was a motor here, right? This is opened up for maintenance or something like that. There's a motor here, and this had a pulley drive, right? Had a motor probably mounted here somewhere and pulleys hooked up to it. So you could actually change the gearing on this, the pulleys on this, so you could change the revolutions per minute and how much air it moves and what the static pressures are. We're going to talk about that later on. So our real interest here is how much air are we going to move and what kind of static pressure is it going to generate so that our hood's going to work right. Okay. You want clean out ports on these things. These things tend to get dirty. They need maintenance. They're moving parts. You want to locate them in the right spot so they're not near fresh air intakes, openable windows. If there are regulations about the discharge, that you make sure you're not somewhere that the heights of the stacks that you design are big enough. They're outdoors, a lot of them, so they're going to deteriorate over time. You got to maintain them. Motors are rated in horsepower, obviously. Horsepower is just a way for you to describe how much energy it's delivering to the system, how much work it's doing. Okay, so a lot of in metric system, they usually use kilowatts in place of horsepower. So the United States will throw out the name. We'll say 2 horsepower. In Europe, they might describe that as by the number of kilowatt hours that it takes to drive it. They make a lot of noise. They vibrate a lot, right? So it's very frequently that you're going to use flexible connections in some spots, particularly when you connect to the fan, so you keep the vibration and the noise down.
I think
Yes.
the other specs on the motor. Can you explain the relevance?
Well, let's see. The horsepower. You see the first arrow there? That first green arrow?
Yeah.
Right. That's the horsepower. Right. 5 horsepower. The second one is the revolutions per minute. Like, in other words, it's designed. It was designed to work with a fan. They put that. They might change that. In other words, if they're working with somebody on designing that, the way that the motor itself rotates when you plug it into. I don't know if you can see it. No, you can't read it here, but it would have the voltage that it would need. It might be 208 volt, 3-phase or something like that. What kind of electrical service that it needs to run and what kind of amperage it expects to pull, right? Which is related to the horsepower, right? And the next number you see there is the service factor. That is basically how much energy you lose. It's an estimate. The fan itself is introducing a loss of energy of 10%. You have to make up for that loss in the fan. And that's kind of like a spot where they warn you about that.
Wait.
We're gonna use that number. We'll see that number later.
This is about the motor, not the fan.
What's that?
This is about the motor.
Well, the motor, it's actually about the fan, but it's on the motor plate because the motor plate was designed to work with that fan.
So the revolutions per minute are about the engine or the
That motor rotates at 3,450 revolutions per minute.
No,
right?
the blade though. On the blades.
The blades may or may not. If you use a direct drive, they might. If you use pulleys, you can change the pulley or a gear drive. You can change the rate at which you can go higher or lower than 3,450, depending on how you gear it. Okay, but that motor, usually when you design these systems, you're designing the motor to fit with the fan. So if you need to turn the fan at 3,000 revolutions per minute in order to get the flow rate that you want, the Q that you want, right? You're not going to buy a motor that's designed to turn at 500 revolutions per minute, because then you're going to have to gear it up so much that it might be a little bit difficult to get it to work properly.
So that person that they play didn't mention anything about CFM or so.
No, all it is a motor turning things. The CFM comes in with the fan. That's part of the fan design. That's just a motor, electrical motor. That's horsepower. Okay, we're gonna get to this.
You said it's direct drive.
What's that? You could have direct drive. You could have a fan hooked right to a motor. Your air conditioner in your home has a motor in it. And when you turn that air conditioner on, two fans move. They're both hooked up to an axle in the middle, a shaft in the middle. There's one on the evaporative coil in the front, one on the condensing coil in the back. When you turn that thing on, both fans start running, and they run at the same revolutions per minute as the motor does. They're both stuck to the shaft that goes through the motor.
When you drive your car,
the
wheels have the same revolutions per minute as the engine?
No. That's why you have a transmission. You have a transmission, exactly.
So you have the same.
I haven't seen any exhaust systems with automatic transmissions, but yeah, you can see. Yes. Yep. Exactly. The gearing can make it go up or down. You have a lot of flexibility, pulleys and gears, right? The only problem is you have limited flexibility because, obviously, if you have to gear, if you have a slow motor and you got to gear it way up, or a fast motor, you got to gear it way down. Then you got to put all sorts of stresses and stuff like that on the gears. May not work all that well. Now you have something called system effect losses, and system effect losses are associated with turbulence in the vicinity of the fan. For instance, right here, there's so much going on in this fan already. Remember, we saw that service factor. We're going to lose 10% of the energy. We're going to lose that. It's going through that fan. We're going to lose that the turbulence that's going on, noise and heat generated in this fan. If you have an elbow or some other connection like that that's too close to the fan, you're gonna introduce what they call service effects, right? And so what's going to happen here is that what you want is you don't want to churn that close to that inlet. You want the suction side of this to be to have no elbows for at least 6 diameters from the fan. So if this is a 12-inch duct, you don't want an elbow before 6 feet, closer than 6 feet to that fan. If it's a 24-inch duct, you don't want an elbow within 12 feet of that inlet. Same on the discharge, except on the discharge you can tolerate a little bit more. It's 3 times the diameter. This is all written down for us. We're going to get to this.
So if that's all the length you had, therefore you should.
Yeah, you absolutely do not want to do this. Put a turn right at the fan. Right, because that really increases the inefficiency.
So you should reduce the duct.
No, you should. If you got to make a turn, you should go in. You should go in straight.
No, I'm saying sometimes you just have limited space.
Yeah. Well, yeah. You want to know something?
How do you compensate?
How many of these pictures are you going to see that have a turn right at the duct, right at the fan? A lot of them do for exactly that reason. They have space.
Right.
But good practice. It's more efficient. You can use a smaller motor, use less energy. If you avoid this, right? If you keep that 6 times the diameter before and 3 times the diameter after, before you make any turns.
Right?
What's that?
The diameter of the duct.
Yes, the diameter of the duct. Yep. We actually have some samples of this right, as we get there. So system effect losses, see it's turning right there. Right? Here's the discharges here on the fan, right? Big 90-degree turn right there. That introduces a lot of loss. The losses there could be as much as 30, 40, 50%, right? At that point. Okay, so that's why you want to avoid that. Here's another one. This is a classic, right? It's going straight on the discharge, but it's turning just before the suction. Again, another one. And the reason why I have so many pictures of these happens all the time, right? Okay. Okay, watch alignments, of course. And why do we have that flexible material between the two of them? Because we want to isolate the vibrations and the noise.
But is that doing anything?
No, it's just like the ductwork. Yes, it's introducing a little bit of loss, but it's so short. It's only a couple of inches. In fact, a lot of times it may even be only a fraction of an inch that really separates them, the two ducts. Okay, we're going to get into these calculations by hand. And then next week, we're going to go through all of these calculations using a prepared spreadsheet, but we're going to learn how to do them by hand first. Okay, so no groaning. No, if you don't do them by hand, you won't learn them. Trust me on that. Won't happen. You plug numbers into the spreadsheet, they won't mean a thing to you when you're done. And it's important you understand this because they really impact the design. So let me see which one I need here. See if this is one. Nope, don't need that one. I think it must be this one. Oh, it got to be this one. Ah, that's the one I want. Okay. Okay, so let's go through this. I'm going to go spin through this. Okay, here's our first part here. Let me see what I got here. I made some notes, highlighted some spots I want to make sure that we went through. Centrifugal and radial fans. Again, we talked about that. The radials are ones that we don't see too often. Okay, so now we want to know how much work, how much pressure that this fan is delivering. Well, we have suction pressure and velocity pressure on one side. We have suction pressure and velocity pressure on the other side, right? So we're not going to look at just these static pressures. We're going to look at the fan total pressures. And we're going to define something called the fan total pressure. And the fan total pressure is going to be the total pressure on the outlet minus the total pressure on the inlet. The total pressure on the inlet is going to be mostly suction, right? So what is this stuff? This is going to be a negative number, right? So a positive number minus a negative number becomes a positive number, so it gets bigger. So if you got -4 plus 2, it's going to come out to be 6. It's going to be a bigger number, positive number. There's always going to be a positive number. Fan total pressure. That's going to account for several things. The velocity pressure and the differences in the static pressure that you need to overcome all the losses that's going through this thing. Okay, so now, that often, 90% of the time, that's what the hood designer or the fan manufacturer is going to want to know to help him size the fan. Going to want to know the fan total pressure. Right? So if you think about this, if the inlet and the outlet size is the same, the velocity pressure is the same going in as it is coming out. So you don't, most of the time you don't have to calculate that. You can calculate this instead, which is the static pressure on the outlet minus static pressure on the inlet. Right? So for this fan where the ductwork is the same size, you can calculate it that way. Right? So if the one I just described, the outlet is +2, the inlet is -4, so minus becomes plus. That's fan total pressure is 6. Okay, so this example right here. The inlet outlet conditions are shown. What's the fan total pressure? Static pressure in is -4. Static pressure out is +4. The velocity pressure in and out is the same. It's the same size duct, same velocity air. So you can forget about the velocity pressure. So the static fan total pressure is 5.4. Make sense? Right? Simple. Good. Okay. Let's take the next. Let's take a look at this.
5.4.
Yeah, 5.4. No, hang on. We don't see the velocity. All we want is the static pressure out minus the static pressure in.
Both are minus.
Right. Yep. A minus becomes a plus, right? So this becomes a plus. That's 0.4 plus 5 is going to be 5.4. Okay. So now sometimes the manufacturer will want to know something else. He'll want to know the fan static pressure. Okay, well, fan static pressure is going to be a little bit different. Okay, so the fan static pressure, we have, instead of total now, we're just thinking static. So the fan static pressure is going to be equal to, fan static pressure is going to be equal to the static pressure and the velocity pressure going out, right? That's the total pressure going out. The static pressure and the velocity pressure going in, that's the total pressure going in, minus the velocity pressure going out. So in other words, what they're looking for is the total pressure, but now take the velocity pressure out of the equation. So I only see the difference in the static pressure. A simpler way to put that is static pressure out minus static pressure in minus the velocity pressure. You know, if it's the same, if you use in or out. Right? So that's the fan static pressure. 90% of the time, the manufacturer is going to want to know something simpler. He's going to want to know the fan total pressure. Sometimes, occasionally, just so you know about it, they'll want to know the fan static pressure. What do you need to do this? Just remember these two formulas. Right? Remember these two formulas, you can calculate the fan total pressure and the fan static pressure. Okay, this shouldn't be a stranger. This is your book, right? I'm working with right now. Okay, so let's see what I got here. There should be another example here. Yeah, E2, did I skip it? Estimate the fan static pressure for the condition FSP, fan static pressure, for the same conditions we had before. Well, the only difference there is that it's going to be the static pressure out minus the static pressure in, which is 0.4, plus 5, minus 1. So now it's going to be 4.4. That's the fan static pressure. That's the portion of the energy that's not contributing to the air movement. That is there. That describes the energy that's being used, the losses that are being overcome because of all the ductwork and turns and so on and so forth. And the velocity pressure is the actual energy that's going into the movement of the air. So one is just basically showing you what the losses are. The fan total pressure is showing you what all the energy is, including the movement of the air. Okay, so that's really more descriptive, fan total pressure, isn't it? Really? Okay, so now you want to actually go now and actually select the fan that's going to do what you need to do. Okay, so we have designed this whole system up to the fan, and we come out of the fan, and now we're designing that out. I'm not actually going to design that tonight, right? Simple enough. Go out, the amount of ductwork you got, the elbows, whatever, the stack, the length of the pipe, and so on and so forth. You do that exactly the same way we did the suction, except the numbers are positive now, right? So we're going to have a fan total pressure that we're going to calculate based on the suction pressure and the discharge pressure of the fan. Discharge pressure of the fan, we're calculating based on how much ductwork we have to go through and turns we have to go through to get the air out of the building. Okay, so
why wouldn't the CFM alone suffice?
Well, the CFM, because we have a certain number of cubic feet per minute, that gives us the amount of material that we're moving, right? But it doesn't account for, that's the velocity pressure gives us that information. In other words, the velocity pressure tells us how much energy is in that air, right? But that doesn't account for all of the losses that we have to make up for throughout the system. The static pressure does that, right? If you just look at the velocity pressure, you're just going to see what it takes the fan to move move that air, without making up for all the losses in the system that you're not going to when you connect that ductwork, you haven't taken into account all those losses because you didn't consider the static pressure that you need. So you're not going to move the fan at that speed. You're not going to meet that Q that you think you're designing it for.
And this is to be able to move whatever contaminant.
Exactly. The whole thing is based on what velocity, what quantity of air you have to suck out at the hood, right, in order to contain the contaminant. So it's all designed around that hood and where that guy's working and what kind of material he's working with. So all of this is designed to accomplish that task. right? And all of the numbers that we're doing here to go through this design, the only reason we're going through all of this is because we have to decide how much our energy losses are going to be so that we can design this system so it actually delivers what we need. Out, out.
Well, not
You
necessarily.
decide where you put it.
Right, you could have
You can filter it out.
Right.
You could have filter that filter. Let's say it's an acid gas or solvent. That could be an activated charcoal filter. So you could filter it. In which case, you could discharge the stuff in the air indoors. Right?
Activated charcoal is coconut shells. Really?
What any source of carbon really ground up
Oh,
is an absorbent. Usually coconut shells because they're cheap and widely used. But no, yeah, he's right. Coconut shell is one of the biggest sources of activated charcoal. So at any rate, for the most part, though, you're taking that contaminant and you're pushing it out of the building, out of the space, right? So it's usually going out of the building. Okay, so now we need to understand we need to select a fan that's going to deliver the fan total pressure that we need and move the quantity of air that we need, right? So I'm going to look, I'm going to, here's a little diagram here. And on the bottom is these cubic feet per minute that I want to move, right? And on the side here is the design pressure. That might be fan total pressure, might be static pressure, whatever, right? So if I create my ductwork system, if I want to move more air, if I want to be further to the right here, I have to generate a larger static pressure or total pressure, right? So this line represents the performance of our fan, of our system really, at different CFM. In fact, you could create your ductwork system, put a damper in, start the fan running, and you could like have the CFM going 1,000, and find the point where at 1,000 what the static pressure is, put it there. Then speed it up to 1,500, put a point there, and you could create this curve if you had a system. If you were trying to evaluate a system, existing system, you could do this if you wanted to. But
what would be the damper?
I'm sorry.
You said a damper.
A damper, something to slow down a damper is basically just a gate, a device like Venetian blinds that you put to keep the air from moving. So it's like a door, basically, right? If sometimes it's a flat piece of iron that slides down into a slot in the duct. That's called a blast gate, right? Sometimes it's a damper is louvers that look basically almost like Venetian blinds that you can open and close a little bit to change the amount of air that's flowing through, right? We're not going to want those in exhaust systems too much, but you could actually manipulate the amount of air that's going through an existing system and see how it performs, what kind of static pressure it generates, and so on. You could create a chart like this for a system that you walked in on and had no experience with to help you understand how it works. I wouldn't worry about it too much right now, but really what we're interested in is the volume flow rate that we need and the pressures we have to generate. Okay, so let me see here. So when a manufacturer creates a fan, he also does this kind of design testing with his fan. They might have a picture. See this right here? This is a picture. Here's a damper at the end here. All he's got here is a very short section of duct on the inlet and no duct on the discharge, right? So what he can do here is he can start this motor running. And he can put a manometer in here so that he can measure a pitot tube. So he can measure how many CFM is flowing through here. So he can say, well, at 100 CFM, the static pressure is this much. At 1,000 CFM, the static pressure is this much. At 1,500, it's this much. See all these points here, all these dots? He can create a fan curve that tells you that if you operate this fan at this static pressure, this is how much air you're going to move. Or conversely, if you want this many CFM, this is the static pressure that you need to generate on this fan. Right? This is the static pressure this fan will generate when it's moving that amount of air. So you need a way to understand how a fan's going to work based on what your needs are for pressure and for quantity of air you're going to move. It's a trade-off, right? So there's trade-off between the quantity of air and the static pressure. The faster you move the air, the more resistance there's going to be, so the static pressure goes up. Yes?
Just to be clear, in terms of the specs that are provided for a fan, do they provide anything in addition to CFM? Like,
Oh yeah, we're getting into that.
Yeah.
We're gonna wait till you see the next. Wait till you see these charts. Okay, so see these charts we have over here? They're kind of interesting, right? Okay, so now these are fan charts. They tell you about fans, about the fan. The manufacturer of the fan creates these charts. So for instance, this manufacturer put together a chart that says that if you run this fan at 500 RPM, right? You can generate this up to this amount of CFM. You can't go over that number of CFM, right? If you run it at 500 CPM, at 500 at a static at 300 at so many CFM, it will generate a static pressure that high. But if you boost it up to, if you're running that many CFM, it'll actually generate a higher static pressure. For the same CFM, if you make it run 1,000 RPM, it'll give you a higher static pressure. So there's trade-off between static pressure and the velocity. And this gives you a view of how many RPM, how fast you got to be turning that blade, that fan, in order to generate the flow that you need and the static pressure that you need. Okay, not only that, but if you notice these fan curves here, right? If you're at the beginning of it here, what you're choking the fan down. You're running high static pressure, but you've got that damper closed down, or you got a lot of resistance in your ductwork, right? So you're choking the fan down. So it has to generate a lot of CFM to get a little bit of air moving. And at this end here, there's very little resistance, right? But you're not generating much static pressure. So actually, in the middle of this curve, right? In the middle of this curve, this area in here, that's where the fan is most efficient, right? That's just past the peak and on the downslope, but not too far down the downslope. This is called the backside of the curve. This is when you're making the fan work too hard. It's trying to move more. It's trying to move air against more resistance than it's really designed to do. So the air is slipping past the blades, and it makes a lot of noise, and it becomes inefficient. So you want to make sure you got a fan that if you need this many CFM and you need this static pressure, that you pick the right fan that like the intersection of those two is within that range. And we're going to be doing that. So it's simpler than it seems right now from my description. Yes. It will be simple.
Are these charts usually like included in the manual, or might
These charts you get from the manufacturer of the fan. I mean, you have them in front of you right now. Okay. You have let's see. I got two handouts.
When you're talking about
These are actual fan performance charts right here. We're gonna be using these in a second. Right. Okay, don't get ahead of me here. Just stay calm.
I'm trying to translate what you're saying into a real life example.
Yeah. Well, we're gonna do it right now. Okay. Now we're gonna use these charts. You might as well pull the charts out now. I'll skip over to that. Okay. We're gonna use these charts to pick out a fan. Okay. So choose an appropriate fan. Don't read past here. Choose an appropriate fan for a system operating point of 10,000 cubic feet per minute and a fan total pressure of 1.5 inches of water. Okay, so remember I told you the fan total pressure is easy for us to calculate, just the difference between going in and coming out, right? And the amount of air that we're moving, we know that because that's how we started. The first thing we did was figure out what Q had to be to make the fan work, that hood work for us, right? Remember that chart for the hood? We calculated what Q is, right? The volume of air. That was the first thing we did, right? It hasn't changed, right? Okay? And that's never changed through this whole system. Q is still the same as when we started, but the fan total pressure is based on how much suction pressure we needed to overcome all the losses and what discharge pressure that we need to overcome whatever's on the other side of the fan, right? So that's our fan total pressure. So our fan total pressure, remember we calculated before at 5.4. Now in this problem, it's 1.5. and Q is 10,000 cubic feet. So let's look at these charts. I'm going to open one up. Let's see if I got one here. Okay, if I can't blow it up. Okay, I'm going to start with this one here. So what's the axis on the bottom here is CFM in thousands. And the axis to the left is, the axis to the right is total pressure, fan total pressure, right? So what's our fan total pressure? 1.5. So 1.5 is about there, right? So we need to go over to 10,000 cubic feet per minute. I'm going to go all the way over here. Here it is. So it's down here somewhere. So 10,000, we go straight up here, and we go across here, right? Well, you want to know something. It's only really close to this curve. And if you notice, it hits the curve all the way towards the top on the back end, right? So that's not going to work very well, is it? It's not in that center section that we want it to be in. This fan won't work very well in this application.
Why?
Okay. Okay.
What happens if it doesn't need a curve?
Okay. We can't use that fan
Why not?
because, here, I'll show you. We
Then
need,
the efficiency is going to be different.
yeah, the efficiency. You don't, that's the whole point. You're the designer.
But it will be probably between 80 and 84.
Hang on. Wait. Okay, wait a second. Okay. So I'm gonna go up here, across here. Right? Okay. So do we want to use it here?
Well, we
Yeah.
can go down.
Huh? We got to go across the 10,000, right?
Yeah.
So we got to go here. So it hits this curve here, right? Roughly, right? We're on the back end of the curve here. We're on the flat part of the curve. We want to be here, right? This fan's not going to work very efficiently.
Why do you want it? Well, the efficiency is
Remember, we had that drawing that showed that the most efficient part of the most efficient range for a fan is through this, is after this dip down. So when it starts to go down, from that point on, not all the way down, but that point on that down slope, not back here. This back end is very inefficient.
The efficiency is that on the top.
Yeah, we're going to get to that. We're going to get to that. We're going to get to that in a second.
So starting from the line
We're going to get to that in a second.
Starting from the line that lines up with the CFM.
Yeah.
And going to the right.
Going, the CFM goes straight up.
No,
And
the
the
line, yeah. So I'm just.
CFM goes straight up, and we're going across from the fan total pressure. And where they meet is the curve, the RPM that you need from that fan to get that CFM and that fan total pressure.
But the line that's in the middle, everything to the right is what you want.
I'm not sure which one you mean. Show me. Come up here, show me.
Okay. So this line.
By the way,
this line right here.
Hang on a second. Each of these curves are the RPM that you need to run the fan to get the performance, total pressure, and the quantity of air.
Okay.
So in other words, if I go across, I'll use a pen. I think I can.
Want it to be in this area.
You want it to be.
What you're saying.
So, okay, sorry. The slant lines are actually, the lines that are slanted are actually referring to the 10.
These lines are the RPMs.
Okay.
Right. The slanted lines are the efficiency.
Well, those the efficiency.
That's the efficiency. See, the highest efficiency here is right here, just past the end of that curve, between here and here, right? So if you start hitting this over here, you're down at 75% efficiency instead of up at 85 or 90% efficiency. So this fan doesn't look to me like to be a great choice. And I started with this one because I knew it wasn't going to be a great choice. How about this one?
So the most efficient part is right where the bear catches the cod.
Exactly. And we start where it goes over.
The bear catches the cod and they want it.
Yeah, exactly. The bear is catching him as he's going. Yeah. So what was the fan? The fan total pressure was 1.5 inch.
Yes.
So you got to go across here, and you got to go see where it intersects with 10,000 cubes per minute. So at 550 CFM, 550 revolutions per minute, you're in an efficient area of this curve. That's up there somewhere. It's probably at 85%. And you're delivering 10,000 cubic feet per minute, and you're delivering 1.5 inch total pressure.
And it has to be within those two lines.
No, it has to be in this general area. should be in this general area.
No,
Let
but-
me go back. Let me go back.
Oh,
Let me go back to, remember this picture here? This is the most efficient area. That's where we want to go. We don't want to be before this because the backside is very inefficient, very noisy, and a lot of vibration. If you go too far down, it's less efficient.
Well, how far down is too far?
Well, you can actually see because of those lines that they have there that are going like that, they track the efficiency, right? So you really want, you have a lot. See, the thing here is that you have an infinite number of choices of fans. There's a million fans you could buy. So you want to buy a fan that's going to work the best, right? It's not like there aren't other fans that'll work, but you want one that'll work the best. So let me go back to this. Okay. So on this particular curve, the Buffalo 730 BL, if I go 1.5 inch, I go across here, I go up to 10,000, they meet at 550 RPM in an area of the curve that's very efficient, right? Would I want to run them, if I ran them at 600, if I wanted to move 10,000 cubic feet per minute, right? At 2 inches, I would run the same fan at 600 RPM.
That would be more efficient.
I don't know if it would. Yeah, it could be. Yeah. But if you look up here, this line represents 80% efficient. This line represents 84% efficient. So in between this is about 82% efficient. But if you start to go down here, you're going below 80. If you start to go above there, you're going below 80.
No. If you go up there, it's doing between 80 and 84.
Yeah.
And it would go one line
Yeah,
further.
you could. Yeah, you're right. You're still pretty good shape up there. But you got to be careful about being on that back end because you get all those other effects, the noise and the vibration. You don't want to be on the back side, too close to the back side of the curve. There's another reason why you don't want to be too far on the back side of the curve. And that is because a small change in the amount of air that you're moving, a small change in the static pressure, right? See how flat it is there? A small change in the quantity of air that you're moving, a small change in the static pressure can make a big change in the quantity of air that you're moving. Right down here, it's like, because the slope is bigger down here. The slope flattens out like that, one can affect the other disproportionately. So a little design change, a little design error can be multiplied. That's one of the other reasons you don't want to be on the back side of the curve, because it's flat. And just a little bit of change in this will make a big change in the amount of air that's going to move through here. Right? So that's how we design. That's the fan that you want for this. Out of the 4 fans, that's going to be. If you look at the other 4, you won't get as good a match on the others. Is it hard to pick a fan? It doesn't seem like it, does it? Right? So what does this give you? This gives you, I think this is a candidate for a fan for us, right? And I think in order to make this work, we got to run it at 550 RPM. Does it tell you what the horsepower of the motor has to be?
No.
Not yet, right? That's the next thing that we have to start worrying about. Okay, so let's continue going through this.
So how much do these cost?
The fans?
Yeah,
They could be anywhere from $1,000 to $40,000. I mean, you're talking about big industrial fans that could be very expensive. It could be. What if you have like something that's a corrosive material? You want stainless steel, right? It could cost a fortune, right? It costs quite a bit of money. But it's, you got to understand. You might be working on a fan this big. You might be working on a fan the size of this room, right? You have a nuclear power plant, and you're trying to ventilate an area or something like that. You have an exhaust system, you want to ventilate an area. You can have an enormous fan.
So this comes from the manufacturer.
Yeah, you get these from the manufacturer. If you go on Google and Google fan curves, right, you'll find, well, what the hell? Hang on a second. Hang on. Fan curves.
Well, you just call them and tell them and they give you
I hate to say this. Chances are they'll practically, to sell the fan, they'll practically sit down and design it for you. Fan performance, okay, let's see. I want to find an actual manufacturer. Let's see. Illinois blower. Did I just see Illinois blower? Yeah, let's see. How do you read a fan curve? Let's see if I can't find some of there. But custom capabilities, products and services, product line. Okay, here's a bunch of fans, right? high pressure, low flow, radial, high pressure, backwardly inclined. Let's see what this one looks like. Okay. Bless you. Okay, it gives you ranges and stuff like that. At some point, I will get to a spec sheet that actually gives you the fan curve specification. Let's see if I can't find that in images. Okay. Yeah, this is a specific fan right here. Inches of water, pascals, CFM. It's a small fan, unfortunately. But you got my. I'm going to try and find some industrial fans. As a matter of fact, let me try that industrial fan. Let's see. Continental fan. Here we go. Available models, performance charts. Select the charts. Dimensional drawings. Come on. Let's see. See, it's saying select the charts diagram tab below. I'm not sure where. Oh, charts and diagrams. Here we go. Here's dimensions. Obviously they got to provide the dimensions with, so on and so forth.
How big is it?
Huh?
How big is it?
This fan is.
You can choose that.
Yeah, they're different sizes. That's what those numbers are on the on 750 and the 850 and the 950. Different size fans. Yeah, I don't want to kill the whole night looking for these things. I'll find some online for you. Okay, so actually, you go to the hood manufacturers. A lot of them will sell fans. So and they'll have the curves there. Okay, so let me move on with this. Okay, I think we did this. We got past. Did I do this one? Take a break. Okay, quick break. 5 minutes. I want to get through this tonight, right? 5 minutes. I want to get out of here at a decent time tonight. Okay, good. 5 minutes.
I have an example that I'm thinking of. I'm trying to put this into, trying to connect the dots.
Yes.
In a basement, we're going to be doing some hammering.
Yes.
So we're thinking of containment and capturing of the dust.
Yes.
So I'm picturing.
Problem with that is that when you start hitting a wall with a sledgehammer, jackhammer. Oh yeah, the dust is going to be everywhere. So how are you going to contain that? So I mean, you could maybe manufacture some sort of like if it's jackhammering here, some sort of hood that you can make out of plywood or something like that. That is right in front of like it's right by where he's jackhammering, so you can suck air away.
We're gonna be in the dock, so to speak. We're gonna set up similar to how they do for asbestos.
Sure.
Wait, you're actually doing that? Oh.
Yeah. The only problem with that is that when they're abating asbestos, they're in the middle of that stuff. That's why they wear the respiratory protection. The ventilation that they use in those systems is to keep negative pressure, so it doesn't escape the containment. Exactly. So they're not really using any ventilation they're not using any capture ventilation, right? I mean, they could conceivably, as he's scraping it, he could have like one of these flexed up fan hoods that could go up against there, like a welder might use, and capture. But you don't see them doing that. They're scraping in the big room, right, and containing it. But they're using PPE as their primary protection. I mean, it doesn't make when you say to yourself, gee, it really would be better if they reduced the dust load to protect themselves a little bit better. But that's not really how they work. They keep that under. They use a fan that's designed specifically for keeping it under a negative pressure, and that's for containment. So not keep it from getting out of the space, but not for removing the contaminant from the air. In fact, it's a HEPA filter, right?
Yeah.
Because you don't want it discharging somewhere where
you're gonna remove asbestos from your basement? Not asbestos. No.
Concrete.
From client's site.
How about water? What kind of jackhammer is it? Pneumatic?
We haven't,
Is it pneumatic?
but yeah, it's gonna be pneumatic.
Yeah, so probably, a shock, it's probably not a shock hazard. So chance if you keep the compressor out of the way, right?
Yeah.
So you could probably use water, spray water to keep the dust down.
It's better not to be pouring water out.
Yeah, I know, it's a mess.
Yeah.
It's messy, yeah. Or you might see if somebody makes a jackhammer with a hood.
With a hood, right? I was thinking maybe that.
Okay.
I don't know. Why? I really
You're getting you're getting anxious. That's what the problem is.
Oh, you?
Yeah, it's not hard. Trust me, it's not hard. It's just you're letting it intimidate you. But by the time we're all done, you're going to have like a set of formulas you could write on one page that you're going to use and the charts. And that's what you're going to use to design it. And in fact, not even going to be that hard because by the time we're done, you're going to be using a spreadsheet that's all prepared for you.
That's right. 5 days.
What's
Chart 5 days.
chart 5? Yeah.
Oh, yeah.
Yeah, that's what it's there for. Put it, that's it. Ventilated. How about ventilated? Mhm. Jackhammer dust control. There you go. That's a hood goes over the jackhammer. And there's you put a vacuum, I guess a shop vac or a HEPA vacuum on there. I mean, just a shop vac, I guess, might work. Hammer dust collection for chiseling. That's a hood. That's a hood. Just like the hoods we're designing for everything else, it's a hood. Yeah, it's for a jackhammer. Let's see what this guy's got. See, here he is. He's using one here. With a shot. Yeah, right there. Oh, it's the same thing. Yeah, it's basically a shop vac. It's a big shop vac. We want some good suction. And a boot. It's a boot, and it's flexible. See, it's got sections so that as you're jackhammering, it keeps a seal between the ground and the jackhammer. Okay, that is automotivepartsfactory.com. Don't ask me why it's there. The Enviro Boot EB1. Yeah, there you go. That's a good idea. Enviro Boot EB1.
And instead of using a shop vac, let's use the top vac that goes right into it.
Yeah. Okay. All right. Yeah, let's get back to work. Everybody sit down. Let's go back to work so we're going to get through this design section. Okay. Okay, system effect losses. System effect losses. These are the losses that come in if you make a turn too close to on the suction side of the discharge of the duct. Right, this is actually the CFM that you get if you don't have the system effect and what you get if you do have the system effect. And that can be like 10, 20, 30% loss of flow and static pressure that's introduced by that extra, by all that extra mess. Okay.
That's expected the efficiency that you get, or
that you're losing efficiency, you have to make up for that. You have to have a bigger fan and motor to make up for that, to keep the same fan total pressure and volume of air. You have to make up for the system effect. If you duct it that way, you have to make up for that loss by sizing up the fan. We're about to find that out. Okay, how many lengths of straight duct should be provided? How many lengths of straight duct? Probably 9 feet of straight duct. Okay. How many lengths of straight duct should be provided into and out of a fan that has an 18-inch round ductwork? Okay, 18 inches at a foot and a half. So it should be 6 times a foot and a half on the suction side and 3 times a foot and a half on the discharge side is how much straight pipe you should have going in and out of there to negate the system loss. And 6 times the diameter going to. Okay. What's a loss factor for? Now look at this. Here's another example. What is the loss factor for a round mitered elbow? What is the loss factor for a round mitered elbow placed right at the inlet to the fan? Now, I wish I had a chart for a round mitered elbow placed right at the. We do. Chart 16. Chart 16. Right? You guys got chart 16? You don't have it? Let me go to chart 16. Oops. But what's a loss factor for a round mitered elbow placed at right inlet at a right inlet to the fan? Right at the inlet to the fan, like this picture right here. Round mitered duct. Mitered means just straight right angle. Mitered, like a mitered frame. You know, like frames not 9 angles. That's the mitered. Okay, and if I go to this chart, if I can find it again, fan curves. Yeah, I'm about to open it here. No, I didn't say that. It's mitered. Mitered is like right angle.
Okay, right.
Yeah, exactly. Yeah. Where is this? There it is. Okay, that's it. Okay, so look at this system effect. This is a two-piece mitered 90-degree section, right? A miter is 2 pieces, right? It's that piece and that piece. By nature, it's 2 pieces. Yeah, they have 3 pieces, but this one is mitered. Yeah, but that's not mitered. Yeah, it is mitered. Yeah, by mitered they mean right angle. Okay, this is a right angle miter. Okay, right, a real miter. Yeah, exactly. So if you're going right to the fan suction with no duct, what's the K factor that you have to add? 3.2. Okay, I think they're going to have another question coming up where it asks you, what is the K factor for a 3-piece elbow? Radius is 2 times the diameter, placed directly on the inlet cone of a centrifugal fan. Okay, so now we got a few. It's 3-piece. The radius of diameter is 2, so it's that, and right at the duct, the K factor is 1. It's not as big a system loss.
Sorry, what is that?
What's that? 2 diameters. Yeah, 2 diameters. In other words, the distance you are from the fan. Right? Notice they only go up to 3. They only go up to 5. Right? Because 6, you don't have the issue on the suction side. Yeah. Yeah. No. Okay. So now we looked at the various things that could give us losses in this whole thing. The loss factor for that, static loss, the loss for being too close, the fan total pressure, and so on and so forth. We already picked out a fit. We got a fan we like based on the fan total pressure and based on the quantity of air that we got to move to Q. We got a fan we like. Now we need a motor for it. Okay, so we need to know how much energy that motor has to deliver. Okay, so the first thing I'm going to calculate is something called AHP, which is air horsepower. That's the amount of horsepower it takes to start the air moving, right? To overcome all the losses, right? And the way we calculate that is the fan total pressure times the quantity of air times the density of air, density correction factor, we're going to ignore that, divided by 6356. What's that 6356? That's an accumulation of all the constants that you need in order to change that into horsepower. Okay? It's the weight of air that's represented by the quantity of air that you're moving per minute. It's the difference, the energy that you have to overcome to get the static pressure. It's a combination of all of that. And the result of that is horsepower. Okay? There's a different number you would put on the bottom if you're in the metric system. Okay, so that's as simple as you got. So if for instance, if the fan horsepower, fan total pressure is 6 inches, and I'm moving 1,000 cubic feet per minute, that's 1,000 times 6 is 6,000, divided by 6356 is roughly 1 horsepower. But that's only what you need to overcome the losses. To actually get the air moving at the speed that you want, you need the brake horsepower. See, that version doesn't get anything accomplished. Just overcomes all the losses, right? Okay, so the brake horsepower is equal to the air horsepower divided by the mechanical efficiency. Didn't I see something about a mechanical efficiency? It was 80% or something like that on that fan chart. So we would get that from the fan curve, the mechanical efficiency. This formula here combines the two previous ones because you're really not interested in the air horsepower. You're really interested in the brake horsepower. It's the fan total pressure times Q divided by 6356 times the mechanical efficiency for the fan operating efficiency, the operating conditions, right? At the static pressure that you're using and so on and so forth, but off of that chart, right? That's where that would come from. That in our case, it would be 0.8, right? So you can calculate the brake horsepower for the motor that you need. Okay, now there's a problem now. Okay, the shaft horsepower. The shaft horsepower makes up for. Remember that motor had a little plate on it, said SHP or S, yes, and the correction factor, whatever it was called. That correction factor makes up for other factors associated with the fan and the motor, right? So that's going to give us now something called the shaft horsepower. How much horsepower we actually need in the shaft to turn this thing to make it work. And depending on you might get that on the motor or on the fan, or you might have to guess at it. If you have to guess at it, use 1.1 for pulley drives on large motors. The one we were looking at was 1.1, right? Use 1.5 for pulley drives on small motors, less than 2 horsepower. Use 1.05 for direct drive motors. Notice that the pulleys introduced a loss versus the direct drive. That's what you're making up for when you have this. The direct drive, you still have some losses, bearing losses, whatever else, that are introduced by that motor or the fan bearings and stuff like that. You're making up for that. See, all along the way here, you're making up for losses in order to calculate how much energy you need. So to calculate the shaft horsepower, you take the brake horsepower and multiply it by that factor K. In our case, let's call it 1.1 because that would happen to be on the plate. So now we got our shaft horsepower. Now our shaft horsepower is nice, except our shaft horsepower might be like 18.5 horsepower or something like that, right? Now our rated horsepower is actually the horsepower of the pump that we want. Okay, so now hang on a second here. Okay, so our rated horsepower. Wait a second here. For small exhaust systems, we usually build in an overrated factor. You want to overrate the motor because you don't want to undersize the motor. Typically, you overrate it like building a bridge. There's a safety factor. You overrate the motor by 33%, by a third. So if your shaft horsepower comes out to be 10, your rated horsepower now is going to be 13. Chances are you're not going to find a 13 horsepower pump, so you go up to the next standard size, which might be 15 horsepower pump, a 15 horsepower motor. Okay. It's kind of a tedious thing, step by step by step, but at each point you're making up for some losses or possible errors that you're introducing. The bearings from the shafts, the system effect losses, and so on and so forth, right? And a safety factor as well. The rated horsepower is what you're interested in. So what have we calculated so far? We have calculated the fan total pressure and the amount of air that we need to move Q. We've used that and various other factors to calculate To select the fan, decide how many RPM we need to turn it at, and select a motor. Now we need a motor that turns at 550 RPM that'll deliver 15 horsepower, right? So we got our fan and we got our motor now. And we can order it along with the rest of the parts that we need, the ductwork, the transitions, the elbows, so on and so forth, and we get it all in and we can start putting it together, right? A rational person would not do that. A rational person would write this all down, check all the calculations, and see if he can optimize the design a little bit. And then perhaps even give the design to the hood or the fan manufacturer so that they can review the design for him. That's the way that you would probably work something like this. Okay, so let's give this a try. What is the required horsepower for this system, and what would be the rating of the horsepower you would choose? So fan total pressure is 5 inches. No problem, we can calculate that, right? We're all okay with calculating fan total pressure, a simple formula, right? Suction pressure, one out minus suction pressure out on the outlet minus suction pressure on the inlet, right? That's the fan total pressure. The out, the out you found you started with 0, right? I mean, the fan is just discharging open air with no ductwork on it. The static pressure is 0 on the outlet, right? But normally you can't do that. You need to get the shit out of the building, right? If it's on the roof, maybe you could do that. But if it weren't, then it'd be 0, right? But if you have to duct it, then you have to figure, I'm connecting an 18-inch duct, 20 feet of it go out here, an elbow, 100 feet of it to go up to the roof, right? So you're calculating just like you did the suction side. You're calculating how much static pressure you need to overcome the 20 feet here and 100 feet here in the elbow, right? So that but it's a positive number now, right? Okay. So you can calculate that. The Q, you can calculate that. That's what you needed at your hood. First thing we calculated. The mechanical efficiency, you get that from the fan manufacturer. That it was on our fan curve as it happened. A correction factor for the type of motor that we're using, right? This is direct drive, so it's 1.1. Yes, exactly. STP. I'm trying to remember what that is. Yeah, but I'm not sure. Yeah, I guess the density correction factor. Okay, and F is our factor for changing all of these things into horsepower from the units that they are. And what are the units? Fan total pressure is inches of water. Q is cubic feet per minute. M is unitless. This is unitless, and we have F. So the shaft horsepower, right, which is from that formula, they skipped all that, the air horsepower and the brake horsepower. Shaft horsepower is FTP, as the fan total pressure 5 inches times 12,000 times the correction factor for the type of motor times the density over, which is 1, over F, which is 6356. That's just the constant we're using, times the mechanical efficiency, which is 0.6. That's 5 times 12,000 times this, divide this, comes out to 17.3 horsepower. Now, what about the rated horsepower? Well, we want to oversize the pump by 33%. So we take the shaft horsepower, 17.3, multiply it by 1.33 to get a 23 horsepower pump for our rated horsepower. So we're gonna pick a standard motor that's 25 horsepower. Okay, so we got our fan, we got our motor. Here's another one. Let's take a look at this one. Estimate the, well, this one they want you to calculate all this stuff, right? And you can go through this one at a time, right? The air horsepower, right, was, we can go back and look at that's the fan total pressure times Q, right, over.
It's just without the correction.
Without the correction factors, yes. That's the first one, right? And then you can, and brake horsepower. You calculate brake horsepower. Then you calculate shaft horsepower. And then you eventually go down and you calculate the rated horsepower. They actually don't even ask you for the rated horsepower. No, and then the rated horsepower for the motor that you want to choose. And it's the same calculation you have there. The only difference is notice that these are metric units, right? So the oh no, they're not metric units. What's that?
EMS,
I don't see it.
the Q,
Q?
Q equals
Oh, it's cubic meters per second.
and what's the S?
A standard cubic meters per second, I think standard temperature and pressure. I think probably
Yeah.
most likely standard cubic. Yeah, and notice that it says the same units, the same for the mechanical efficiency, the correction factor for the motor, and and the density factor. It says the same because they're all unitless. And the F factor that you're dividing by instead of 6356 is 102.2 because you're working in the metric system. And it'll give you, instead of horsepower, what's it going to give you?
Kilowatt?
Kilowatts, right, exactly. Exactly right. Okay, so so I'm going to come back to this part because it's a little bit of a tangent over here. Okay, so I want to go past this for a second for us to come back and say to yourself, okay, I now have designed this entire ductwork system. The only part of this that next week we're going to broach is a lot of times they'll have one fan and one motor, but they'll hook up several hoods to it. So your system might have junctions in it where you connect another hood into your main ductwork and work your way back up to the fan. So we're going to go over that. I'm not going to try and kill you guys with that. Maybe we'll do at least one, somehow or other, do at least one example where there's two hoods on the same fan and motor so that you guys can see what the process is of calculating it. And we won't do it by hand. We'll do it using the spreadsheets. Okay, just so you know. But this is what the way that everything you've seen up to this point gives you everything you need to design a system with one hood and one fan and one motor, right? And get it wherever you want it to go, move it wherever you want to go, get the right transport velocity, get the right capture velocity, and so on. Okay, so now at this stage you got to start ordering parts. Okay, well the parts the ductwork is a certain material, certain diameter, certain length. The hood you're going to order as a unit, and so on and so forth. But now you need the fan and the motor. So in order to specify the fan and the motor, you're going to want to tell the manufacturer what kind of fan you want. You want axial or centrifugal, forward curve, backward curve. And there's considerations there, right? Remember we talked about the forward curves one versus the backward curve one, what the issues might be for particulate or for noise. Okay, the volume flow rate, right? That's your Q. Your fan static pressure or total pressure. Usually total pressure. Sometimes they'll want fan static pressure. That was the alternative calculation. The temperature and density of the air that you're going to be moving. It's going to be standard temperature and pressure, or is it going to be heated? What kind of material are you going to be moving? Dust, aerosol? Is the fan going to be affected by this material? Is there a mist or vapor? What kind of inlet configuration are you going to have? They're going to be system effect losses and so on. How are you going to connect to this thing? There may be options on the fan. You may be able to order it with different size collars and different connectors and so on and so forth. You may be able to order it so that it comes in one side, goes straight out, or you may get it from the right angle and go straight up. Wheel type, what material, for instance, what motor and size, which we just figured out how to calculate. What drive type, going to be pulley or is it going to be a direct drive? Physical character configuration of the fan housing. Do you want it to point out because you're going to go out? You need to go out that direction before you turn up to go outside of the building, or do you want it to go straight up because you're going to place the fan somewhere where you can go straight up out of the building? Physical access to the fan housing. Depending on what kind of material you're going to have, how long you expect this is going to last, may want to be able to service this thing. So you may want hatches on here, and so on. Clean outs, hatches. What kind of bearings? Maybe the material that you're trying to move may impact what kind of bearings and seals that this thing may have. It could be, if it's a solvent vapor, you may want to make sure that these seals are compatible with these particular vapor that you're working with. Flexible couplings. You're going to need flexible couplings to control noise and vibration for sure. Okay, what are your noise requirements? Is it a factor? Is it not a factor? And that'll impact the operating efficiency and what kind of fan you use, what forward facing, backward facing. How you're going to mount it? Is it going to be mounted on the floor solid, or is it going to be on vibration dampers? Have you ever seen like big motors They usually don't mount them directly to a concrete floor. They're usually on springs or rubber platforms so that the vibrations don't get transferred to the floor. Rain and weather protection. It's going to be indoors or outdoors. Stack requirements. How what kind of support the fan may need, so on and so forth. Okay, so you have a whole bunch of things besides the motor and the fan design itself that you have to communicate to the fan manufacturer, right? That you either have to consider yourself or you have to warn him about. Okay, so I'm going to go back in a second. So what I did was I made up a fake example. Okay, let me go. I actually put these all on here. Okay, here's an example. Provide the specifications for a fan and motor to be installed on an exhaust system serving a metal cleaning bath using flammable solvents. Might be a slot hood or something like that, who knows, right? Controlling noise is a consideration, right? So you know that going in. And you know it's a flammable material. You have to move 12,000 cubic feet per minute of air. The static pressure at the fan inlet has to be minus 1.5 inches. At the outlet has to be 0.5 inch, and the velocity pressure is 1 inch. Right. So I didn't tell you the diameter of the duct, did I? Right. I didn't because you don't need it because I told you the velocity pressure. You could actually calculate it because if you know the velocity pressure, you know what Q is. You can figure out from the velocity pressure what the velocity air is. So if you know Q and you know the velocity, you can figure out A, the cross-sectional area of the ductwork. But you don't have to. Nobody asked you for it. Okay, calculate fan total pressure, fan static pressure. Choose an appropriate fan from the Buffalo fan curves. Identify the fan RPM and the efficiency. Assuming that no system losses are associated with that, you're gonna go in straight and come out straight. Okay, calculate the brake horsepower, the shaft horsepower, and specify the rated horsepower of the pump motor of the motor that you're going to need. Summarize the specifications of your fan and requirements that you information above. You'll need to provide the and the information that you'll need on pages 20 and 21. In other words, the materials, all that kind of stuff. I told you it was flammable. So what kind of fan do you need? Yeah, intrinsically safe motor, right? Sealed, intrinsically safe motor, and you'll need fan blades that are non-sparking, right? Okay, right? So like that, and then it's a gas, right? So that might impact. Summarize, and then put that all together and upload it. Okay, that's not too challenging, right?
I've been uploading stuff, but I've not been getting any feedback.
Huh? I'll start to give you some feedback. I'll make sure you guys start to get some feedback.
Can we get like up until next Wednesday?
Yeah, you can have until next Wednesday. Yes.
Why? Okay.
You can have until next Wednesday.
No, I'm just telling you. Where's the next
We can ask questions.
Oh, right.
Yeah, we can ask questions.
Yes, it makes sense.
You know what you should do? Upload it by next Tuesday. Ask questions in class, and I won't grade what you uploaded. I'll wait until Wednesday to grade it. To grade your last version. I'll only count the last version.
The last thing I submitted
Yes.
I uploaded it, but when I went to put another version on,
Yes.
it wouldn't allow me, so that's why I have to send you.
Oh, yeah, I saw that. You did email me the picture. What I'll do is I'll make sure that it has unlimited submissions. Yeah, that's okay. Okay, no problem. It might have been set at 2 or some default or something like that. But I'll make sure it's unlimited. Okay. All right, good. Oh yeah, let's call it a night. I think I just wanted to mention, you can read this on your own. There is a way for you to calculate, for instance, if you have a fan that's operating you designed this at 550 RPM, you designed it all right, and you said, oh shit, it's not moving enough air, right? There are formulas there where you can take the increase in RPM that you put on a fan and convert it into the change in static pressure and volume of air that it'll deliver and the horsepower that you need. Okay, So you can actually kind of adjust for this. So that's the nice thing about having pulleys or gears is that you can actually make some changes if you need to. Let me just show you what they look like. Okay, and you can actually go in here and you can play around with these. So for instance,
We can send this.
so Q1 over Q2, Q1 over 2Q is equal to N2 over N1, right, which is the RPM. In other words, if you double the RPM, you double the amount of air that you move. Makes sense, right? If you double the RPM, the square of that, so you double the RPM, you multiply the static pressure by 4. It's the square of the ratio. And the power requirements are by the third power. It would be 2 times 2 times 2 would be 8 times the amount of power that you need to run that fan if you're going to double the RPM. Right? But you'll be delivering a lot more air and stuff like that. So those are just some formulas that relate the RPM. You know, you're going to design a fan for a certain RPM. But if you want to evaluate, oh, look at this fan we have here in this. A lot of times you go into a situation, you go into a plant, they have an existing exhaust system. It's not working well. It's not doing what it needs to do. So you have to evaluate how it's working and what you need to do to fix it. And one of the things you may need to do to fix it is maybe change the motor and increase the RPM on the fan if they're not getting enough suction, right? These formulas will help you figure out how much you have to increase the RPM, how much bigger a motor you need to do it, right? So it relates Q, the RPM, the difference in the RPM before and after, to the difference in the quantity of air, to the difference in the fan static pressure, to the difference in the amount of power that you need to drive the whole thing. Okay, just so you know those formulas are there. Right? We don't need to worry about that now. That's a correction thing. No. And you have this book, this book, right? This book. This is this guy. All his life, he was designing industrial ventilation systems. You have in that book the cumulative knowledge that he learned, that he accumulated over 40 years. He's an old geezer. He's living in Phoenix now, I think, right? So you have that accumulation. You have this material here. So trust me, if you spend a little bit of time learning this, maybe for 2 years, 3 years, you'll never hear anything. You won't touch anything that has to do with that. And then one day, somebody's going to say, "Shit, we got a customer. It's got to do something about this exhaust, this ventilation system for his workers. This plating plant. Has all these slot hoods. They're not working right. He doesn't know what he's got to do. They've been cranking up the fan speed, but it ain't helping because he's not putting a bigger motor in, right? It's because it needs more power requirements if you do that. So it ain't helping. You don't know what to do with them. Maybe there's something wrong, so on and so forth. Anybody know anything about exhaust systems? Bingo, you're Johnny on the spot. And you will still have the materials that we're using in this class on your bookshelf there somewhere, right? So even though you remember nothing from this class, right? When you pull those books out and start going through them, it'll start to remind you. And what did I do here? I went through this chapter with you. There's nothing I did here that is not in this book already, right? Even the examples I did, for most part, were the ones in this book. I might have changed a number or two, but not really.